Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
I'm a geologist, but I work on the geology of other planets. So currently I'm on 2 NASA missions going to small bodies in the outer solar system.
Any other interesting mysteries about asteroids that you're studying? I had heard that some people want to mine, land on and mine certain asteroids. So is there like a critical site limit that's necessary for a craft to be able to land on it?
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Dr. Daniel Britt. He goes by Dan. He's the Pegasus Professor of Astronomy and Planetary Sciences, part of the Department of Physics at University of Central Florida. We're going to talk about our planetary orbit, interacts with the appearance or disappearance of ice ages on our planet and the history of climate. Dan also consults periodically with NASA on some of their various missions, so we may get into that, we may not. Dan, thanks for coming.
Sure, happy to be here.
If you would, tell me a bit about the current work that you're doing. What are some of the projects you're working on? And then, we'll pick one to focus on. Maybe
I'm a geologist, but I work on the geology of other planets. So currently I'm on 2 NASA missions going to small bodies in the outer solar system.
Okay.
And, what we do is try to analyze the data output of these missions and plan for these encounters and try to puzzle out what we see in the newly viewed worlds.
So what missions are going where? Are they going to asteroids or planets, or where do you study?
Yeah, I'm mostly an asteroid guy. So I'm on the Lucy mission, which is going to the Trojan asteroid swarm, which is co-orbits with Jupiter. And then I'm on the New Horizons mission. They went to Pluto and then on to a small Kuiper Belt object called Arrokoth that's way, way out in the solar system, almost 50 astronomical units away, 50 times the Earth's distance to the sun.
Okay.
So I get around.
What are some of the different kinds of asteroids that are out there?
Asteroids come in everything from soggy dirt clods to pieces of steel. There's a huge variety. Yeah.
Huh. So some are like completely metallic almost, and some are made of what, dirt?
Dirt, yeah. Soggy dirt clods, yeah. Basically, what you've got is you can get, this planet differentiated. That is, it heated up, the iron dropped into the core, silicates floated to the top, created the lithosphere that we live on. Well, the same thing happened on asteroids. So if you smash open an asteroid, what you do is you get pieces from the core, the mantle, and the crust. And so there are asteroids that have completely melted. And if you're holding a metallic meteorite in your hand, that came from the core of that asteroid. And since you're holding the core in your hand, a piece of the core, obviously the rest of it is smashed into small pieces.
There's maybe a stupid question, but do asteroids come from a common source? I know not all of them would, but is there a majority that come from X or Y source that we observe?
No. The thing is, these are leftovers from the accretion of planets. So they come from basically the same source the Earth did, that is the nebula that used to surround the sun and created the sun and the planets. And these are things that just never accreted into something bigger. There's a bunch of reasons why that didn't happen.
But what about impacts, that where a piece of a planet, a small piece was, the moon was impacted, let's say, and a piece blew off and went into space?
Yeah, that happens all the time. So we get meteorites from the moon.
Different?
Say again?
Is that something different from an asteroid? Is that
No. An asteroid is any sort of natural thing that orbits the sun. If it's a meteorite is a piece of an asteroid that happens to be sitting on the ground. So you put the same thing in orbit around the sun, and you can call it an asteroid.
Okay, so a meteorite is an asteroid that's entered Earth's atmosphere and landed on the planet somewhere.
Yeah, just a very small piece.
Gotcha. And then are comets considered asteroids, or are they a different creature for some reason?
Well, there's a continuum of stuff, and comets are on one end of that continuum. They're full of water and frozen other stuff like CO and carbon monoxide, carbon dioxide, and dust. So, in a real sense, there's no real difference between an asteroid and a comet. They're both small bodies. It's just that comet is a term that comes down to us from the earliest days of human communication, as you saw these things, the ancients saw these things in the sky.
Okay. If you look at, I don't know if, I'm sure people have done maybe a survey of all the asteroids out there. Are most of them clods of dirt? Are a lot of them metallic? Like, what's the breakdown of the different types of asteroids that are out there?
Yeah, we do surveys, but the best way to look at these things is what arrives on Earth in the form of meteorites. And most of them are stony, rocks of one sort or another. And then 5 or 6% are metallic. And probably a large number of the asteroids are just so weak and so full of ice and volatiles that they never get through the atmosphere. So there are things that are ice-rich. There are things that are essentially dirt-rich. There are things that are rocky, and there are things that are metallic.
What are some of the rarest kind of asteroids ever seen, or meteorites ever seen?
Well, the rarest are ones that come from other planets. So we've got meteorites that come from Mars, and also meteorites that come from the moon.
Okay, and those are rare.
Those are highly prized. It's kind of a cheap planetary sample return mission when you find a meteorite from another planet.
Okay. Are there ones that you can tell have come from outside our solar system? And if so, how could you tell?
Well, there are grains in these things that are probably what they call pre-solar. That is, that they were never melted during the accretion and concentration of the nebula that the sun evolved out of. Because what happened was that the nebula had heated up and vaporized or melted things. And so you can look at the isotopic ratios of some elements in these grains. They'll have isotopic ratios that are distinctive from the isotopic ratios you see widespread in the solar system. But you don't really see whole rocks from other solar systems. You see a few grains.
Oh, why? Why is that?
Well, the thing is, it's mostly function relative velocity. And so things that are coming from other solar systems are going to have very high velocities relative to the velocities of this solar system and Earth. And so it's very hard for them to survive. Back when you were accreting the sun, it wasn't just a one-off event. The nearest star right now is Alpha Centauri, which is about 3 and change light years away. In that same space, when you were accreting the sun, there were probably 2,000 to 5,000 stars. So you had lots of solar nebulas, and they were exchanging material all the time. But the material were, grains of dust, very small grains.
Okay.
And it's certainly possible that we might have exchanged other, whole chunks of asteroid or comet with some of these other solar systems. It's just hard to find, and it wouldn't be that abundant.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now, back to the show. All right. I know it's a general question, but how is an asteroid changed by it becoming a meteorite going through our atmosphere, landing, etc.? Is there, like, what's preserved and what's not preserved about?
Well, yeah, what happens is that moving at cosmic speed, so, 20, 30 kilometers a second, it's really cooking. And in order to slow down to terminal velocity, it essentially takes all that energy of motion and converts it to frictional heat as it's going through the atmosphere. And so a lot of this just burns off and vaporizes. Somewhere between 85 and 95% of the mass of a meteorite is lost on atmospheric entry.
Oh, wow.
So, what you get is what's left over. Rocks typically don't have very good heat conductivity. So you're not going to melt the whole thing. You just end up with what's called a fusion crust. That is a millimeter thick or so layer of glassy stuff, where that's the remnants of the stuff that's been melted off during its atmospheric passage.
Okay. What can you tell again from meteorites that you've studied about asteroids that we can't get to, that are way out in space?
Yeah, what you're doing is you're seeing the variety of mineralogy in the asteroid belt. So it's hard to get to asteroids, but the meteorites are samples of all of this stuff. It's just like any geologic sample. You take a sample, you take it back to the lab, and you learn in detail what's going on in that rock formation.
Yeah, why do we have an asteroid belt? Why is there an area where they tend to, the Kuiper belt, I guess, and I don't know how many other belts, but why do a lot of asteroids accumulate in certain areas in our solar system?
Oh, it's gravity. The problem is that Jupiter is very big. Jupiter has like 85% of the mass of all the planets. And so once Jupiter accreted, its gravitational influence made it hard for anything else to form within several astronomical units of Jupiter. So it basically disrupted the formation of anything else nearby. Sure. And so the asteroid belt between Mars and Jupiter is really all the stuff that could have formed into a planet but never did because Jupiter got in the way.
So consequently, around the sun, an X number of lengths away from it, whatever, I don't know what unit of measurement you'd say, is there an asteroid belt there too? Because
everything inward from the inner planets are too close together to really allow many asteroids to have stable orbits. So there are asteroids that cross interplanet orbits. It's just that they don't live very long in geologic or astronomical terms. They whack into stuff. They run into the planet.
The sun is what, like 99% of the mass of our solar system.
Oh yeah.
And then that's kind of funny how it is, like the 80-20 rule, and then Jupiter, like you said, is 85% of the mass of all the planets.
Yeah.
So there's interesting hierarchies here.
Oh yeah. And that strongly affects how things work.
Okay. So what are you studying about the asteroids you're looking at or the meteorites you're looking at? What are you trying to ascertain?
Well, the idea is to understand what their mineralogies are, how they evolve, how they can be of use to us in future exploration, how you can avoid having them whack into the Earth and eliminate all civilized life, things like that.
What is the tendency of, so asteroids that become meteorites, is there anything that's, again, they share in common? Why do certain ones, besides size, they either burn up or they don't? Is there anything else that would make it more likely that an asteroid would enter the Earth's atmosphere?
Well, it's just kind of a random walk through orbits. And so meteorites and small asteroids hit the Earth all the time. Small stuff is a lot more common than big stuff. So, and what happens is these things are moving so fast, they're so energetic that quite often they explode in the upper atmosphere. Essentially, their kinetic energy flashes to thermal energy, and you do that fast, it's called an explosion.
Oh, okay. So they become like superheated very quickly and they blow apart?
Yeah, something like that.
Oh, interesting. Okay.
And, you get kiloton-sized flashes in the upper atmosphere every month or two.
Huh.
There are people that care about explosions in the atmosphere, and so they collect that kind of data.
So if you look at speeds or velocities, what's the difference between smaller asteroids and larger ones? Is the velocity the same, or?
Yeah, the velocity is going to be exactly the same. It's just governed by celestial dynamics.
Are there classes, though, of asteroids that are a lot faster than others or slower?
Well, typically comets are faster because they tend to have eccentric orbits. So they're moving from orbital zones that are farther out in the solar system, and that makes them faster in the inner solar system.
Do asteroids pick up speed? Do they go near enough to certain planets to use gravity?
Oh, sure.
Around?
Yeah, the Earth's gravity will accelerate something that gets close to it, for instance.
Okay.
So the Earth-Moon system will add extra kilometers per second of velocity as you get pulled into the Earth's gravity well.
Or like you mentioned, Jupiter is incredibly massive. So
yeah,
are there asteroids that go somewhat close to Jupiter that get accelerated a lot more by its mass than others?
Oh yeah. Again, this is just a Newtonian dynamics question. People calculate these orbits all the time.
Okay. So again, what questions are you trying to answer in regards to asteroids that you feel are very interesting to look at?
Well, how they're put together, so their basic structure. One thing we found that most small asteroids are just piles of shattered rubble. So you can imagine it's just kind of a sandbar in space. And because they've been hit by other asteroids and shattered and reassembled by self-gravity. And so basically all the small asteroids that we visited so far are piles of rubble. And that kind of structure is interesting. We weren't really sure that was the way it worked, but now we're getting pretty sure. Say again?
I'm sorry. Do they have a grain size, various asteroids, because they've been blown up and reassembled and blown up and reassembled?
Well, that's something we're looking into, but it's typically a range of like boulders, cobbles, pebbles, sand-sized stuff, dust-sized stuff. There's a hierarchy there.
Yeah.
And it's typically the result percussive impact. So you actually get more or less the same kind of size relationship that you do if you just hit something with a sledgehammer.
Oh, but again, the gravity is pulling them back. They're reassembling.
Right.
So does it look like as they break, reassemble, like how many cycles do they go through that? And what interesting features does it create, if any?
Well, it creates all sorts of strange features. These things tend to have, the really rubbly stuff tend to have equatorial bulges if they rotate fast enough, for instance. And that's just, it's acting kind of like a rotating water droplet in that case.
All right. Yeah, I had heard there was an asteroid Oumuamua that supposedly came from outside our solar system.
Yep.
Did you study that at all, or is there anything interesting about that one?
Well, there's lots interesting. It came from outside of the solar system, so that was the first one. It's been another one since then. We're just getting better at picking them up and tracking, which is why we're seeing them now. People that do theoretical analysis of this sort of stuff figures you should see, with any luck, you should see, one or two every year. It just depends on how thoroughly you look for these things.
Yeah.
And Oumuamua, and the way you tell is that it's got an orbital pattern that is not bound to the sun. So it's going to go whooshing through the solar system and out the other side.
Okay. Any other interesting mysteries about asteroids that you're studying? I had heard that some people want to mine, land on and mine certain asteroids. So is there like a critical site limit that's necessary for a craft to be able to land on it, not just gravity-wise, but, and move around wise?
Yeah, well, the issue is that the asteroids that you want to use for mining are going to be small ones, because typically what you want to mine are the volatiles that are locked in the crystal structures of the minerals. And the ideal asteroid for that would be about 5 or 10 meters in diameter, so fairly small.
Oh, really?
But the idea is you put essentially a waterproof bag around them and use solar energy to essentially cook out the volatiles out of the minerals.
Oh, wow.
And that way you get about 10% of the mass of the asteroid out in water.
Okay.
Which is very valuable for outside the Earth's outside the Earth's atmosphere, very valuable in orbit. It can be used for fuel. It can be used for life support. It can be used for shielding.
But how would you, roll up alongside one and stay with it and be able to put like this shielding around it and cook stuff off and harvest it? And it seems like a very, very complicated type thing to do. I guess some asteroids tumble and,
they'll tumble, but the whole thing is that you can just match their tumbling. It's just position keeping and orbital dynamics. So that's fairly, it's not trivial, but it's not that hard of a problem.
Okay. So it is possible. I mean, what about the, maybe this is just fanciful, but is there any need to land on certain asteroids, or is it even possible and, to mine them, or is that like a whole different ballgame than what you're talking about?
Well, it's easily possible to land on these things. And, mining it is not that much of a problem. People are developing technologies for these things. With really small asteroids, they have such a tiny gravitational field that you're mostly formation flying with them rather than landing.
Okay. I mean, so have people mined asteroids, or there's still not enough technology developed yet, or, where are we at with that?
People are developing that kind of technology. Haven't done it yet, but, people are working on it.
Okay. Fair enough. What do you hope to see in regards to asteroids in the next, 5 to 10 years? Like, are you a big proponent of the mining, or are there other things that you think are more important to discover about them?
Well, there are always things that are important to discover, especially in how they're put together and how they actually work in detail. But I think that in the next 5 or 10 years, you're going to find private companies that would be interested in harvesting small asteroids for their volatiles and selling that to other companies in Earth orbit.
Yeah, what are some of the the most beneficial or useful type minerals or compounds that come from asteroids?
Well, the metallic asteroids, of course, are 95 or 98% iron and nickel. So you can get metal from those guys. Ones I'm most interested in are the volatile rich asteroids, which they have essentially clays. They're made out of clays that have hydrated compounds built into their crystal structure. And so you can suck out 10 or 15 weight percent water out of these guys.
Okay, and the water is the most useful thing, or
well, I think it's probably going to be the most useful thing in the near future, because it can be used for a lot of different applications: fuel, life support, things like that.
So an asteroid that's just the right size to be able to be, position tracked and bagged and, water sucked out, how much of a payload would you get on average?
Oh, you'd probably be getting something like hundreds of tons.
Oh, okay. So it's very significant, and you wouldn't have to launch it from the surface of the Earth.
Right.
So that would.
Yeah. The whole point of this is that
for a long time, or what would that do?
Well, yeah, there are people developing thrusters that directly use water as fuel, and multiple tons of fuel are very attractive in Earth orbit.
Yeah.
Because otherwise, you have to fire them up with a rocket at $2,000 or $3,000 a kilo.
Yeah, I would think against the vacuum of space, any surface water would be gone instantly. So I guess any water would be trapped inside. And so you'd have to bag it and crack it open, otherwise it would all dissipate instantly, right?
Well, yeah, any surface water. But remember that this is water that's locked in the crystal structure of the minerals.
Oh, okay.
And so you have to break the minerals apart. It's not that hard, and there's proven ways of doing it. It's just you have to do it, and that's why you bag the asteroid to begin with, is you don't want those volatiles floating off into space.
Right, makes sense, yeah. Anything special happen when water is exposed to the vacuum of space? I mean, I guess it freezes instantly and
it volatilizes very fast. It doesn't freeze so much as it goes into vapor.
Okay. Is there any appreciable amounts of water vapor floating around in our solar system, or not really?
No, not really. Well, there's basically the solar wind is full of things like hydrogen and other atoms, but that's very diffuse. So there's not really an appreciable amount of stuff in any one chunk of. There's not a harvestable amount of anything there.
Yeah. Okay. Well, very good, Dan. Where can people go to find out more about your work
Well, I make simulants for planetary surfaces. So you can look me up at the University of Central Florida, or can look up the Exolith Lab, and that has a website, Exolith, EXOLITHS, exolithsimulants.com. So EXOLITH simulants.com, and you can see some of the stuff we make for the science and engineering community.
Okay, very good. Well, Dan, thanks so much for coming on the podcast. I really appreciate it.
We didn't have much of a chance to talk about climate change, though.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.